Hi guys, welcome to our third video in chapter 7, which is all about the elements. In this video, I'm going to talk about the properties of the D and F block elements. So this video should be a little bit shorter because these elements are less important for high school studies because they are more complicated and they do involve a lot of quantum mechanics to really understand their chemistry. But we can at least talk about some of their more basic properties that we can work with. So to begin, I do have highlighted our D block transition metals. That's the top part in the periodic table. Then we have our F block, which is the inner transition metals. And that's the lower part of the periodic table, right? So that should be review. We have talked about those. I do want to make a note that we, as chemists, we call this first row here, the first element in that is called lanthanium. So we call these the lanthanides, the lanthanide series. And then we call the second row, which is headed by actinium, we call these the actinide series. So that's just and they're both series. And so they kind of are treated as if they were a group, just like the noble gases. However, we know they're in the same period, not actually in the same family. But because they're so big and have such strange properties, we just throw them all together. We lump them up. So let's begin by talking about the transition metals, the D block metals here. And I have actually a couple of pictures here to show what these elements look like in their pure states. So going from left to right, we actually have the periodic table, that third row of the periodic table. We have our first row of the D block, right? So we have scandium here, we have titanium here. This blue one is vanadium. This yellow one is chromium, manganese, another white one. Then we're up to iron as this red one, or orange one, cobalt's this red one, nickel's this weird green color, copper's this cool blue one, and then finally we have our zinc is this other white one. So unlike many of the other families of elements, our D block is going to have a lot of optical activity, right? So also to the left here, I have four different solutions. All of these solutions contain vanadium. So the difference between the blue, green, purple, and yellow colors comes from vanadium with a +1 charge, +2 charge, +3 charge, and then a +4 charge would make the yellow. So the different colors are caused by the different charges on our vanadium. But I think that kind of illustrates how transition metals are somewhat interesting because they have a lot of optical activity, right? Those partially filled d orbitals allow these things to be very colorful for quantum mechanical reasons, right? That's kind of beyond the scope of our class we can talk about, but this is awesome. This is actually my wheelhouse as a chemist. I am what's known as an inorganic chemist. So I spent a lot of time studying transition metals, specifically iron and vanadium, and how they interacted, what they did, all that kind of stuff. So let's talk about some of their chemistry, right? So the formation of ions here. They are metals, and this goes for transition metals as well as your inner transition metals. And I am gonna, this is bolded, I'm gonna highlight it. I want you to highlight it, right? This always form positive ions. So transition metals will always be positive, which simplifies things for us greatly. Now, the charges they assume are fairly complicated. And I just want to point out that you could have all of these transition elements can easily have +1 or +2 charge because they can lose their s electrons, right? They have 2 s orbital electrons in their valence shell. They could lose those pretty easily. Those partially filled d orbitals can also lose electrons and form +3 or higher charge. And for many of these transition metals, if you have a very strongly electronegative element, you can form +6 charge, which is a very highly charged particle. I've even seen elements with +8 charge, but that is very rare. So that's how they tend to form charges. And something that you should note in this, at the end of this video, I'm going to talk about how to predict the charges of any group, except for our transition element. So let's make a note. Charge will be given. So instead of asking you to predict what the charge of iron would be, I do need to actually tell you it is iron with a +3 charge or iron with a +2 charge. Predicting what its charge will be is beyond the scope of a high school chemistry class. Another property of many metals in transition, and of course our inner transition metals, is that they are magnetic. So I'm going to highlight this as well. This is a key property of metals. I believe you already know this. And a specific term that we should write down is ferromagnetism. And this is the attraction of a material to I'm going to actually change this to a permanent magnetic field. Of course, I can't spell permanent right. Never thought I would be able to, but anyway. So that is called ferromagnetism, and the word ferro, the prefix ferro here, this is ancient Greek for iron. So the reason iron's symbol on the periodic table, I'll scroll down for a second, iron's right here, it is Fe, because that stands for ferrous, which is the Greek word for iron, right? Like Ferris wheel is an iron wheel. So ferromagnetism is the type of magnetism that you're most familiar with. It is what happens in iron. So if we look over here, and this happens again because of those partially filled d orbitals. So I actually have two examples here on the right-hand side. I have an example. A shows you a typical piece of iron. And you can see in here, it's got some arrows. Those arrows are actually showing our electron spins. And in a normal piece of iron, you can see those spins are all, going random directions. They're not aligned. And then what can happen is when I put my iron in a magnetic field, since those d orbitals are partially filled, those electrons are able to move and align themselves with a magnetic field. So in B, we can see the, let's say the spins align with magnetic field. I say mag field, right? So they align with the magnetic field, and this is what allows a piece of metal to experience magnetism. Not every metal has partially filled d electrons, and therefore not every metal is magnetic. A good example would be aluminum, which does not even have d electrons. So that's a part of the reason why aluminum is not magnetic. Moving on from magnetism, we have our sources of transition metals. So definition for you, another vocab word here, metallurgy. This is the branch of science that studies and designs methods for getting metals out of ores. And we already talked about what an ore is. So you have these, this is a ladder here, and this bucket is massive. If you've ever seen like the Star Wars prequels of I think it's the Attack of the Clones, that big factory, that was a metallurgy factory, right? So they have to extract the metal from the ore, and then they use it to build robots. But I digress. So here I actually have a map that shows all or many different locations of where we get some important metals, right? So you can see the United States kind of barren here, but we go to Canada, we can get nickel, copper, niobium, gallium, tantalum, zinc, cadmium, and cesium. So we get a lot of stuff from Canada. If you wanted to get some tin, you'd probably go to Indonesia. If you wanted to get chromium, you could go, of course, to Russia, Turkey, anywhere like that. So this just shows that different metals are found in many different locations throughout the Earth. All right, I am finally ready to tell you guys about what is called the preferred charge. And this, we needed to talk about all of the families before we could really get here. Please highlight this. This is so important. This is what is going to play a central role in the next 2 units. Okay, so preferred charge is the charge that allows an ion to attain a stable octet. And you know you have a stable octet if you have the same number of electrons as your nearest noble gas. So if we consider elements that are in the noble gas column already, we know that their preferred charge should be 0. So since they are so I'll do green. I'll write the preferred charges above these things. And you may want to make another annotation on your periodic table for what those preferred charges are. But because your noble gases already have those electrons of a noble gas, they don't want to change anything. So they don't form ions. So they have a preferred charge of 0. If I go back 1 column to my column number 17, my halogens, these atoms are 1 electron away from a noble gas. So if they gain 1 more electron, right? So fluorine has 9. If it gains 1 more to get 10 electrons like neon, they will have a stable octet. And in doing so, they will gain a negative charge. So they'll gain 1 electron. Going back 1 more, I see my oxygen. And for oxygen, I can see if I have 8, if I gain 1 and 2, I will get up to neon. So oxygen's preferred charge would be -2. And remember, this is everything in this whole column. So this goes for sulfur, selenium, tellurium, polonium, and whatever 116 is. Nitrogen's a little bit further away, but I see nitrogen. It goes, I've got 7. It could go 8, 9, and 10. So I could gain 3. So nitrogen will form a -3. Before we get to our column 14, I'm going to actually think about if I started at neon, what if I go up 1 element to sodium? Well, sodium here with 11 electrons, it would be easier for sodium. If you think about it, it can either lose 1 electron and go back to neon, right, and empty that valence shell, or it could gain 1, 2, 3, 4, 5, 6, 7 and go up to argon. Since it is easier to lose 1 electron, that is what sodium will do. It will lose that electron and therefore go down to 10 total electrons, which matches neon. And our sodium column will have a preferred charge of +1. So where it was -1 for our halogens, our alkali metals lose electrons, therefore it will be positive. Moving on to my group 2, my alkaline earth metals, beryllium, we'll do magnesium. Magnesium's at 12. It can either gain 6 to go up to 18 to get to argon's noble gas configuration, or it could lose 2 and go back down to neon. And since losing 2 is easier than gaining 6, magnesium's column and the alkaline earth metals will form a +2 preferred charge. Skipping my d orbitals, right? Remember, they have variable oxidation states. I'm going to go to aluminum and boron. And I see that aluminum now has a choice of either losing 3 or gaining 5. Since losing 3 is easier, your aluminum will be +3. So we've got some nice symmetry going on. We've got -1, -2, -3, and we've got +1, +2, and +3. And then our noble gases, of course, are 0. And that leaves us with our column in the middle, which, of course, is the most important column for life because this is the more flexible column. It is 4. It can either gain 4 or it could lose 4. So for our column 14, we can say plus and -4. So I have a plus minus sign at the same time, indicating that carbon can either gain or lose electrons. So again, now we know, and by the way, for things in column 4A, I will have to tell you if it forms a plus or -4 charge. I'll have to give you that information. So what we've done is outlined the preferred charges for our representative elements. And we've said everything in column 13 has a preferred charge of +3. Everything in column 16 has a preferred charge of -2. Again, this will play a very important role when we move on to our next chapter about ionic bonding. All right, guys, that's it for this video. Have a great day, and I'll see you guys in the next one.